or clarification regarding with anything. Okay, so you can ask anything. And yeah, before I will forget. So all of you here are CPEs, right? Since section naman to ng CPE, wala naman siguro nangyalo. So there will be a coming event on this coming of, I'm not sure if it's October 16 or October 15, but yeah, the second week of October. So there will be a quiz bowl programming, call this one, like I don't know, but it's a programming competition. Okay, so the languages are C sharp, C++, C, and then Python, I guess. So I can't remember anymore, but I will post it or I will announce it later on, the complete detail. And then we also have a Mobile Legend tournament. Okay, and the last one is Beach Bowl. So there's a total of 4 events. Okay, so the deadline of uh registration is October 9, if I'm not mistaken. So those are the things that I can remember while we're having a meeting. So yeah, the only people or the only students that can join are CPE students only. Okay, so I will post the mechanics later on or the full detail of those events. Okay, so just prepare just in case that you're interested. So please represent UC. So yung the opponents will be IPSU and ano pa ba yung iba? BSU, ay hindi. I think BSU or BCU. So there were 4 universities who will compete in those events. Okay, so I just can't remember the exact names of those schools. Okay, but yeah, so certain Gingan will choose I think one team for the programming, and then one team for the pitch bowl, and then one team for the what is the other one? But yeah, one team for those 3, and then 2 teams for the Mobile Legends. So that's the only event that will accept 2 teams. Okay, and then the others will only accept 1 team. So yeah, I hope you guys will join. Anyway, so medyo matagal pa naman. The due date of registration will be on October 9. So you guys still have like 2 weeks to think of where you are going to join. So just try. Diba? Maybe kasama ka. So may mga prizes din. So, and certificates of course. Anyway, so any questions so far regarding with the event? None? No clarification? All right, so anyway, let's just talk about that one some other time. So for this meeting, we have to finish this chapter 4, Clippers. So as you guys can see, we have 63 slides in here, but don't you guys worry. Most of the topics in here are super easy, and then most of the examples are super easy. Okay, so let's start with the question: what is a clipper? So this one is a device. So you could say this one can limit, or this one can remove, or this one can prevent some portion of the waveform input signal voltage, of course, that waveform that we're talking about, above or below a certain level. Okay, so in other words, the circuit which limits a positive or a negative amplitude or both is called a chipping circuit. So this clipper can be also called a chipping circuit. So again, we can say that this one limits, or this one removes, or this one prevents. So any of those terminologies. But let's just say that this one can limit a positive side, okay, or a negative side, or you can limit both. Okay, like you can clip both sides. All right, so we have 5 types of clippers, of course. wherein this one clips the positive side, and then this one clips the negative side. And then we also have a shunt or a parallel clipper. So of course, this one is also composed of positive and negative clipper. Okay, and then the last one is of course the combination, which of course will clip both sides, the positive and then the negative. So sometimes we also call this one combination. All right, so let's start with a series positive clipper. So to make it simple, okay, so series positive clipper clips the positive side. That's it. Okay, so I will leave the reading part to you guys. So mostly this is just the saying about the connectivities of your voltage input, wherein this one should be connected to the negative and this one should be connected to positive, and then we have here the resistance and so on and so forth. Okay, so yeah, this one clips the positive part of your waveform. So this is your voltage input. Of course, you have the complete waveform, positive, negative, positive, negative. But in the output, so this one only accepts negative, wherein our positive side was clipped, okay, or was removed or was limit. Okay, so again, just a continuation, but same scenario, okay, or same explanation. So are we clear so far regarding with series positive clipper?
Yes, sir.
Okay. So this one's same with with our half wave rectifier, okay, where it only accepts half of it, okay, which only is negative. All right. So here are the combinations that you guys need to know, of course. So it's very straightforward. So during the positive half cycle, of course, we have 0 volts since it doesn't accept. Okay, just wait a second, guys. 1 minute. Yeah, just wait a second, guys. Tapon yung tubigan ng pusa ko. So, nagkalat ng tubig dito. Anyway, so going back to our discussion. So again, during the positive half cycle, of course, we have 0 volts. So it completely clips the positive side. And then during the negative half cycle, we have now here the reading of the VI plus VD. So VI is the voltage input and then VD is the voltage threshold. Okay, so you guys will know later on why this one is plus. Sir, isn't it that this one should be negative because we're going to deduct the voltage threshold? So later on, you will see that this one is really plus, not negative. Anyway, so yeah, that's it for the series positive clipper formulas. Okay, so let's have an actual example. So we'll solve for VO, and this one is a series positive clipper, which is ideal. So again, if it's ideal, then there is no voltage threshold of this diode. So during the positive half cycle, of course, we have this connection positive to negative, and then negative to positive. So as a result, this will become an open circuit, right? Are we correct, guys?
Yes, sir.
So if it's an open circuit, what will happen to our VO, or what will be the reading of our VO? Dito na nga yung
Zero
sagot.
volts.
Wala pang sumasagot. Okay. 0 volts, of course. Okay. So very obvious. Again, if it's open circuit, of course, there is no flow of current. Okay, so the reading of our VO right here, okay, or the voltage across right here is, of course, 0 volts. And during the negative half cycle, so this one is ideal. So this one is negative to negative, positive to positive. So if that is the connection, then this will form a forward bias, okay, or a closed circuit. So if that's the case, then we have a flow of current in here. Okay, and if you guys are going to take a look on this one, so we have a negative polarity. So negative first going to our R1. Okay, so in here we have here a negative 5 volts reading. Okay, and then going back to our formula, we have VO is equal to VI plus VD. So as you guys can see, we really added voltage at threshold. We didn't deduct that one, okay? Though it won't affect our answer since this one is ideal anyway and this one is 0. So yeah, but just in case this one is not ideal, so you still have to add this one, okay? Since this one is negative and then this one should be deducted to this negative, okay? So that is why we have a plus sign in here. So negative 5 plus 0 is equal to negative 5 volts, okay? And in here, just to make it clear, all right. So in here, this VO right here is the same with, so let's say this is your positive probe and then the negative probe. So the probe that I'm talking about right here is the, what do you call this one? VOM or the voltometer. Yeah, voltometer, VOM. Ano pa ibang tawag natin doon? Like multimeter. Okay. But yeah, the one that can reads a current or a voltage. Okay, that one, that uh, a certain device. Anyway, so this is where you're going to put your positive probe, and then this is where you're going to put your negative probe. So in here, if you're going to read the voltage across this path right here from here, let's say from node A to node B, of course, the voltage reading is negative 5 because that is the only voltage that will flow on this entire circuit. So that is why VO right here is equal to negative 5. Okay. So this one now is different from our previous topics wherein we only read the VO at this certain part. Okay, like whatever it will pass through this path right here, let's say a resistor or a diode or another voltage source, then whatever is that, upon reaching this node right here, that is the reading of VO. But in here, it's not. So you have to completely pass this entire circuit, I mean this entire path right here from, let's say, node A to node B. Okay, so I hope we're clear with this one. All right, so moving on, for you guys to appreciate, the series positive clipper. So this time, we still have the same example, but this one now is non-ideal. So if it's non-ideal, of course, it will now eat or it will consume a certain amount of voltage. So if it's a silicon, then it will consume 0.7 volts. So during the positive half cycles, nothing will change. This one is still a reverse bias, okay, or an open circuit. So as a result, we still have a 0 volts reading on this VO. So are we clear with that one?
Yes, sir.
Okay. And then during the positive half cycle, so the only additional one is, of course, the value of your voltage threshold, which is now 0.7. So same example, same everything, but in here we now have the value of your voltage threshold, which is 0.7. So negative 5 plus 0.7 is negative 4.3 volts. Okay, so the reading now of this path right here, let's say from node A to node B, is negative 4.3 volts. So as a result, at the positive side was clipped, and then we have a deduction of voltage from 5 to negative 4.3. Okay, so you could say that the positive side was completely clipped, and then the negative side was clipped partially due to this silicon diode. That it's a certain amount of voltage. So are we clear with example number 2? Any questions so
Yes,
far?
sir.
If ever that you have a question or clarification, so just let me know, okay? All right, so let's now move on to the series positive clipper, but this time it has now a bias. So when we see bias, it's just the additional voltage source in our circuit. So this bias, can be divided into two, or can be classified into two. So we have a positive bias and then a negative bias. So I think it's very obvious when I see positive bias, it's just a matter of polarity. So positive first and then negative. And then when we see negative bias, we have here negative first and then the positive uh, polarity or a positive connection. Okay, so here are the effects of those biases. So if we have positive bias, so it will clip, partly of our waveform in the positive side, and then I think you still have the same negative waveform. Okay, oh, excuse me. But in negative bias, it completely clips the positive side, and then I'm not sure with this one because this one depends on the value of our VI and then our bias voltage. So this one, it could deduct, or it could add more or amplify our voltage input. So depending on the value of our bias voltage. Okay. Well, anyway, since this one is situational, so it would be better if we're going to discuss this one in an actual example, okay, with real values and what will really happen. All right, so here are the things that you can consider upon, if we say positive half cycle and then it's a bias or positive bias. Okay, so you can use this formula, VO is equal to VB minus VD. So later on, we'll discuss why it's VB minus VD. And then we have here negative half cycle, which, we have a VO, which is equal to VI plus VB plus VB. Okay, so without a further ado, let's start with example number 3. So this one is a series passive leaper with positive bias. So let's start with ideal circuit first. Again, when it's ideal, so there is no voltage threshold. So in here, if we are going to analyze this one, so positive is connected to negative and the negative is connected to the positive. So as a result, this will become an open circuit, right? Or this part is now like gone or removed since we have no connection in here. But on this part, okay, we still have a voltage source, okay, or a bias voltage, which is say this VB. So we still have a reading of on this spot on this a certain VO. So 2, okay, minus 0, or this voltage at threshold right here, since this one is ideal anyway. So as a result, we have a reading of 2 volts, okay, on this VO. So that is a voltage that is flowing on this circuit right here. So are we clear with this one? And why is it 2?
Clear na, sir.
Yes, sir.
Okay, so if ever that you're maybe confused, so just let me know, okay? And then during the negative half cycle, so as you guys can see, this one now is negative to negative and then positive to positive. So as a result, we now have a closed circuit or a forward bias connection right here. So we now have a complete flow of current on this entire circuit. So in here, you can just simply use Ohm's law, or you can just simply use Kirchhoff's law. So in here, there's two possibilities, it's either, clockwise or counterclockwise. But again, just know the rule of voltages. So whichever is the highest, that is the one that, that will dominate the entire flow of current of the entire circuit. So in here, 5 volts is greater than 2 volts. So as a result, this is the correct assumption, and then this is the incorrect assumption. Okay, So if we have that flow of circuit, let's just label this one. So this one is -5. This one is 0 since this one is ideal. And then we have here -2 volts. So I'm just simply considering the outer sign, okay, of those voltages. So -5 plus 0 plus -2 is equal to -7. So what I did is, I just simply analyze this one quickly with a Kirchhoff's law. So that is why we have here -7 volts. Okay, -5 plus 0 plus -2. So are we clear on how did we get this -7 volts? Okay, great.
Yes, sir.
So in here, this one is, yeah, you can use this one, I guess, but you can just simply remove BD since this one is ideal. Okay, so this one is not heavily reliable, but yeah, you can still stick with this one. Just make this BD 0. Okay, what I'm trying to say is do not heavily rely on this formulas because sometimes this one is incorrect. Due to the arrangement of your bias voltage and then your diode maybe. So let's say maybe your bias voltage is right here and then your diode is right here. So you cannot apply this one anymore. So just stick with, with your analysis. Like, you can just simply use Kirchhoff's law. With that, you'll get the correct answer. Just like what we did in here. Okay, so when we say VO, it's reading on this part and this part. So upon calculating, this voltage right here, we've got a -7, right? Anyway, so that's it for example number 3. Let's now move on to the example number 4, but of course this time it's now non-ideal. So everything is the same. All we need to do is deduct or include the silicon diode or the this diode voltage threshold. So in here we have 0.7, of course. So 2 minus 0.7 is equal to 1.3 volts. Okay. So in here, if you guys are going to take a look on this one is a little bit confusing, but you will understand that that's how it works. Okay, so let's start with a graph. Let's say 0 volts. So this is a DC voltage. Okay, this bias voltage right here. So it's consistently 2 volts. But in this V1 right here, or this VI right here, voltage input, this one is an AC voltage. So as we all know, if it's an AC, so it will start, to a 0 voltage first, and then going up until it reaches the peak voltage, which is the +5. Okay. So initially, of course, let's say during the 0 volts, or let's say 1 volt. Okay, let's say 1 volt right here. Okay, 1 volt voltage input. We now have a reading of 2 volts on the entire circuit. Okay, so as you guys can see, positive is connected to the positive diode and the negative is connected to the negative diode. So as a result, this will become a forward bias. Okay, so if it's in a forward bias, so there is now a flow of current of this entire circuit. Okay, so as a result, we have here 2 volts minus 0.7 volts. So going back here, let's say into this voltage output reading, we now have a positive 1.3 volt. Okay, so that is why we have here our positive 1.3. And then that's the reason why we have to deduct this 0.7 volts, even though the reading of VO is only this part. Okay, that is because of this analysis. Like initially, during the 0 volt or 1 volt, okay, we now have a reading of 1.3 volts all in all. Okay, and then after maybe some time, it will now reach 2 volts. Okay, see 2 volts right here. It will now reach 2 volts, and then this will now become completely a reverse bias. That is because this one now is, let's say, equal or higher than our bias voltage. So as a result, it will stop the flow of current of the entire circuit. But nevertheless, we now have a reading of 1.3 volts in this specific time. Okay, so for the first maybe millisecond, we now have a reading of 1.3 volts, and then all throughout, let's say after 5 seconds, let's say 1 volt is equal to 1 second. So ganun yung incremental value na lang. And yeah, so positive 2 to positive 5 is now a completely reverse bias. So that is why it prohibits now the current on this entire circuit. But then again, nevertheless, we already had a reading of 1.3 volts before that. So that is why the voltage output reading in here is 1.3 volts. So are we clear with that one?
Yes, sir.
Okay, so to those other, to those who are not giving a thumbs up or a response, so just let me know, okay? So nakakabahala kasi mas maraming hindi nagta-thumbs up. Baka 3 lang or 4 lang nakakakuha and then nagpo-proceed pa rin tayo. So mas maraming concerns or questions kapag ganun. So mas mahirap solusyonan kumbaga kapag natapos na 'tong module and then dami niyo palang katanungan. Anyway, so that's it for the positive half cycle. So let's now move on during the negative half cycle. So let's get this one. All right. So analyze first the circuit. So we have negative to negative, positive to positive. So the same with this one, positive to positive, negative to negative. So all throughout, this diode will be in a forward bias connection. So as a result, this one is completely closed or completely, there's a complete flow of current on this entire circuit. So in here, just simply take a look on which one is higher. So if it's a VI, then we have this flow of current. If it's the VB, then we have this flow of current. But since 5 is greater than 2, so we have this flow of current. So we have negative 5 right here, and then we have here positive 0.7, and then we have here negative 2. So just simply add those, Kirchhoff's law. So negative 5 plus 0.7 is negative 4.3, minus 2 is negative 6.3. So it's a reading of this VO right here. Okay, so are we clear with negative half cycle?
Yes, sir.
Okay. All right. So great. Let's now move on to a series passive clipper with negative bias. So in here, this one now is super simple. Whatever you've learned in a series, my bad. This one is still a series positive clipper, but this one now is a negative bias. So yeah, vice versa. Whatever you've learned in a positive bias, just reverse that one. Okay, all you need to do is reverse the polarity of this bias right here. So if it's plus, just make that one negative. Okay, if it's negative, just make that one positive. Okay, so it's just a matter of changing the polarity or the signage of your bias voltage. Anyway, so during the positive half cycle, so we still have a 0 volts reading right here. And then for the negative half cycle, we have this formula right here. But then again, this one is not heavily reliable, especially if we have a, uh, a value, okay, on this voltage threshold, okay, or a value on this bias voltage. So we'll still have the reading on the positive half cycle, okay. So anyway, so let's have an actual example. So let's start with an ideal diode first. So just check the connectivity. So positive to negative, negative to positive, and then negative to positive, and then positive to negative. So as a result, this one, is completely reverse bias or an open circuit. So that is why we have a reading of 0 volts are right here. Okay. So are we clear with this one on why this one is 0 volts? Okay. All right, so moving on to the negative half cycle. So just check again the connectivity. So negative to negative, positive to positive. So it's now a forward bias connection on our voltage input. But on the other side, on the bias voltage, so negative to positive, positive to negative is still a reverse bias connection. So all throughout our voltages will only flow or will only dictate by this voltage input right here. Okay, so since this one is ideal, so after passing through this diode, we still have a reading of -5. Okay, but after taking a look at that one, so it will still pass through this bias voltage. So -5 plus 2 is equal to -3 volts. So yeah, that's how we've got this -3 volts right here. So are we clear?